So hello together. Today I want to measure the capacitance per unit length of a cable, a coaxial cable. I have here a cable, it has a length of 1 meter. Then we have here a multimeter, which we can use to measure the capacitance. And here I have a special connector, which is able to give the transition to our coaxial cable. So, and in the first step I select the capacitance to measure the capacitance. So now I selected this and I insert our connector, and the connector shows in capacitance of round about 2 picofarad. And now I can connect our cable to this measurement equipment, and then we measure round about 104 picofarad. So in total our cable has 102 picofarad per meter. So hello together. Today I want to start with the exercise, and in the first problem we will discuss a coaxial cable which shows a characteristic impedance of 50 ohm, and this coaxial cable is called RG58, which is usually used in the laboratory, and it shows a capacitance per unit length of round about 100 picofarad per meter, and the manufacturer gives the attenuation of the cable at 100 megahertz with an attenuation of 16 dB per meter. And in our first point we want to calculate now its inductance per unit length. And to calculate the inductance per unit length we use the equation for the characteristic impedance. And since we know the characteristic impedance and also the capacitance per unit length, we can solve for the inductance per unit length, which would be given by this equation. And of course then we can insert our numbers here. We have here the 100 picofarad per meter times the square of 50 ohm. This gives, for the inductance per unit length, 252.5 nanohenry per meter. So in the next step we want to calculate the relative permittivity epsilon r of its dielectric. We know, or I showed in the lecture, that according to Maxwell's theory you cannot choose L and C arbitrary of each other, but they must show a certain relation. So this can be used to calculate now the dielectric of the cable. And also if we insert here the numbers, we end up in a dielectric of round about 2.3. Around about 2.3. This is the permittivity of the cable. And in the next step we can now calculate its damping constant. So the cable manufacturer, they will give the damping constant normally in dB per meter, and in the lecture notes I give an example, and if I transfer this example to this problem, then we end up for alpha in this equation. And if we insert our numbers, then we will find that alpha is 1.85 10 to the power of minus 2 1 over meter. And of course now we can think, where does the damping come from? And in our case I want to assume that the damping is a result of the resistance per unit length, and we ignore the conductance per unit length in this example. So we can find for alpha according to our lecture notes, it's R prime divided by 2 ZC, and also this can be solved for R prime. And if you calculate now R prime, then you will end up in a value of 1.84 ohm over meter. It's very important to see that this is now the resistance at 100 megahertz, which results also which results from the skin depth of the material. So in the next step we come to our problem 2. So in this problem we have a lossless transmission line which is terminated with a load resistance of 25 ohm and an amplitude of the incident wave is 5 volt. So in the first step we want to calculate the reflection coefficient of the load resistance, which is in this case quite easy. So we know the reflection coefficient of the load can be calculated by RL, the load resistance minus ZC, divided by RL plus ZC, which results in minus 1/3. According to the lecture notes, we can now also calculate the maximum and minimum voltage on the transmission line. And in the lecture notes we found that the maximum voltage is given by the amplitude of the incident voltage times 1 plus the absolute value of RL. In our case this is 5 volt times 4/3, which results in 6.67 volt. In the next step we can calculate now the minimum voltage on the transmission line. It's again the amplitude of the incident wave times 1 minus the absolute value of RL, which results now in a value of 3.3 volt. Having these two values, we can also calculate the voltage standing wave ratio, and we will find the voltage standing wave ratio is given as Umax over Umin, and in our case this is 2. So this finishes the calculation of the two problems.